nice office.
Corona.
These things rule. Whatever, send them to Mars. Hello, Stan. If you know who I am, then you know why I'm here. I know everything. I guess that makes two of us, huh? Look, sir. You, unplug the sun. Oh, sorry.
Hey, the sun is within the clouds, and that's because we're not seeing a physical sun.
We're not seeing a physical sun. You know, so again, this so-called projection that you see here, it's in the clouds, it's a projection.
Solar outbursts get their start deep within the core of the sun. The sun's immense gravity squeezes hydrogen atoms. The pressure and heat rises, causing a fusion reaction in which the hydrogen atoms crash together, merging to form heavier atoms, like helium. This process gives off heat, which rises in plumes to the surface of the sun. The SOHO spacecraft can see the result by recording ultraviolet light. It detects a wavy pattern of gas on the sun's surface, along with a super hot halo of gas called the corona. The white regions are places where the rising gas suddenly escapes, forming loops that rise into space and fall back. There are times when this smooth sequence of generating and releasing energy gets bottled up by a magnetic field spun off by the sun's spinning turbulent core. Using data from the sun's exterior, scientists have modeled these fields as they erupt all around the sun's surface. These field lines twist and loop around, while heat rising from the sun's core follows these lines toward the surface. The magnetic fields can also stifle them. That's where sunspots form, where the surface is relatively cool. Below, the heat and pressure begin to build. SOHO's detectors have managed to catch the moment when the energy is suddenly released. A shockwave travels rapidly outward, like a solar tsunami. These waves stay on the surface of the sun as they travel around it, but they are a sign of what's about to happen. They signal the start of a coronal mass ejection, or CME, a massive eruption of particles in hot gas. Using a coronagraph to block out the bright light of the sun, you can see how violent our star can get. If you see a CME spreading out in all directions from behind this artificial eclipse, you'll know that satellites and power systems on Earth are going to get hit hard. Especially if that scintillating cloud of bulk plasma is weighted in the direction of where Earth will be in its orbit in about 24 to 36 hours. Whether it's a light solar breeze or a titanic coronal mass ejection, the sun sends a wave of energetic particles crashing into Earth's magnetic field. When the energy builds to a critical threshold, hordes of charged particles move out along field lines, wrapping around the Earth, and finally flowing in. When these charged particles are channeled and concentrated around Earth's poles, suddenly, with a snap like an electric arc, they'll induce huge jolts of strong current, strong enough to wreck spacecraft and burn power stations on the ground. Or these charges can simply dazzle observers with a silent, awe-inspiring light show. Waves of charged particles sneak through in the far north and south, creating colorful curtains of light called auroras. The magnificent aurora borealis in the northern hemisphere, and the gorgeous aurora australis in the south. But as lovely a light show as this is, it means there are kilovolts of electricity in the air, looking for places to get to ground. And as more and more of the ground around Earth gets carpeted with conductive metal, the chances are that all that juice will fry something vital to humanity.